ISO Kolkata welcomes you all to the sixth Science Talk of the month. Today's speakers are Jacob Nasterski and Dr. Chris Zaleski, both from the Loughborough University. Jacob has completed his BSc in Chemical Engineering at the Loughborough University, being a top student in his year. He is currently pursuing a PhD at Loughborough University focused on quartz crystal microbalance for soft matter sensing. Dr. Chris Zaleski completed an MSc in biotechnology in Poland, followed by an MSc and PhD in chemistry obtained at the University of Leicester. In 2020, he joined the research group led by Dr. Ghosh from Loughborough University. He has broad research interests ranging from material science to charge storage devices. So today we have been utterly honored by their presence and would love to know about how to make efficient batteries. So let's go and take the fun ride. Thank you.
Okay, thank you for this very kind introduction. We're delighted to present our work. I'm Jakub. This is Chris. Greetings to all our listeners, and let's begin. So our work is sort of divided in two parts. One is the electromechanical resonators, the other is battery electrolytes. So the way we organize this presentation is we're gonna go through the basics of resonators first. I will do this part, and then I will give it over to Chris to present the battery side of things, and in the end we'll combine it and show you what interesting things we can do when we put the two together. So let's begin. So this story actually begins with vibration, and vibration is everywhere. It's one of the most common phenomena in the universe. It's used both in nature. Your heart vibrates, the waves, their vibrations. And it's widely used for all sorts of engineering applications as well, for watches, for musical instruments, even your electric toothbrush vibrates. So what's important for us is we want to measure those vibrations. And the way we do it is we interface piezoelectric elements with electricity to read frequency. And how do we do that? I'll show you how we do it. It starts with quartz crystal resonators. They are thin discs, as you see, between 30 to 300 microns. So it's more or less the scale of human hair. They are made of crystalline quartz and covered by gold electrodes on both sides. So that's nice, they look pretty, but what can we do with them? And the key is piezoelectricity. So when you apply voltage to those gold electrodes, something interesting happens. The top side of the crystal wants to move away from the bottom side of the crystal. In other words, the crystal shears. When we apply alternating voltage though, you can imagine that it will shear back and forth. So I've made a little animation here to illustrate that. So you can imagine that this line is this line in this crystal. So we apply voltage, and this is what happens to the quartz. By the way, you'll see later that it actually moves much quicker than that. The key thing here to remember, which will come in useful, is that the electric current drawn by the electrodes increases when the oscillation amplitude of the quartz increases as well. And the way we connect it to those electrodes is we use a PCB board setup. We connect cables, and the crystal electrode wraps around. So one of the electrodes is connected here, the other electrode is connected here. So don't be scared, this is just a little bit of mathematical background to sort of explain where we get the values from. And the basic way to model the quartz crystal is a spring mass damper system. For the mechanical engineers out there, I'm sure you will be familiar with this picture. The spring, the stiffness models the elasticity of the quartz. The C, this is the damping, models the friction. So this is both external and internal friction. And just simply applying Newton's second law. I'm trying to. Yes, we get this equation. And in vibration mechanics, what we like to do is use those constants omega, which is the natural frequency, and gamma, which is the width of resonance, as I'll show you later. So using those constants, plugging into this equation, we get this, which is a second-order linear differential equation. And the solution to this is a simple harmonic motion like this, just a sine wave, with an amplitude A. And the omega, the frequency of the sine wave, you see, it's exactly the same as the frequency of the force. So the force wants to force itself on the mass, and the mass has to move with the same frequency of the force with some sort of amplitude. And this amplitude, as you see here, it depends on the, so omega 0, this is the natural frequency of the system, it doesn't change. And omega of the force, we can sweep it. So as you see, if the frequency of the force is close to the natural frequency of the system, the amplitude increases. That's resonance. So this is the phenomenon that you might be familiar with, vibrating bridges and that sort of things. And another thing that influences the amplitude, as you see, is the gamma. So that's related to friction. And you can see it on this graph with, here are presented in terms of the quality factor. So you can see that when the gamma is big, the quality factor is small. So with big gamma, small quality factor, the peak is very small. With small gamma, big quality factor, the peak is very high. So that's quite intuitive. That the more friction we apply, the less amplitude it's gonna be. But okay, so this is just the physical background. So but now let's see how, because we want to measure it, and let's just look at the numbers here. So the typical natural frequencies of quartz crystals that we use for QCM, that's quartz crystal microbalance, is around 5 to 50 megahertz. So that's 50 million cycles per second. 50 million cycles per second. So maybe you remember in physics class when you were measuring the natural frequencies of pendulums. All you have to do is sort of count the cycles and divide it by the time, and you know the natural frequency. But how do you count 50 million cycles per second? And also, it's impossible to measure this mass, stiffness, and damping directly when we use quartz crystal for measurements. And instead of doing that, we can use a technique of applying an equivalent electrical circuit. So remember what I showed you a few slides ago, that when we oscillate this crystal with alternating current, as the oscillations of the crystal increase, the current drawn by the electrodes also increase. So the current will be proportional to the displacement of the quartz. And this is just the equivalent electronic circuit. We have the resistance, the capacitance, the inductance, and these are you can compare them to stiffness, to damping, and to mass. And if you look at the equation for this, it's the same form as we've seen the mechanical equation earlier. You can see that when the frequency of the current is close to the natural frequency of the system, we also have this resonance peak. And the constants have their equivalences. So the resonant frequency here is 1 over square root of LC. The gamma is R over L. So when we so this is the actual reading from one of our instruments. So we applied the alternating voltage close to the resonance frequency of our crystal, which is around 13.3 megahertz. And you see that the current is maximum at a certain frequency. And what we do is we can fit this current numerically. And numerically, we can simply extract the RLC values corresponding to this curve. And when we have the RLC values, we simply calculate the natural frequency and the gamma. So just to summarize those last 3 or 4 slides, if you were a bit lost, that's all you need to know for the rest, for the next part. And also an important thing to note, this gamma, which is this R over L, corresponds to the width of the resonance peak at half of the power. And in vibration mechanics, or in QCM at least, what we prefer to use is gamma, the big gamma, dissipation. And this is just the small gamma divided by 2. We call it the half bandwidth. So you see it appear in measurements later. Okay, so that's really nice. We've established that we have those quartz crystals which oscillate at really high frequencies. We can measure them. We can measure them by interfacing them electronically. But as engineers, we're always interested in how we can apply this, or more specifically, how we can apply this to solve complex problems and get simpler answers. So let's look at this. So consider the position of very thin metallic layers. That's often used in electrochemistry and other industrial applications. So say for some reason we want to deposit copper on gold, and this copper deposition is maybe 100 nanometers thick. And if you ever used one of those micrometers, you know it's quite difficult to measure 100 nanometers. But what we can do instead is do this deposition on a quartz crystal, and while the deposition is happening, we can measure the frequency parameters of the quartz. So we can keep doing those frequency sweeps. We can keep fitting the vibration properties and see how the natural frequency and dissipation is changing. So the natural frequency, if you remember from this one, depends on mass. So with increasing mass, the frequency is expected to go down. So this is a curve of time passing here, with the thickness of the position increasing. We can see the frequency is going down, 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 down. On the other hand, the dissipation is increasing, so we can see increasing friction. And that is because the copper, essentially, this deposition is less slippery than gold, so it will cause more friction on the quartz, and we can sense it here. Then, we can actually, when we measure those frequency shifts, we can directly use it to calculate the mass of the copper deposition using what's called the Sauerbrei equation. We just need to know the properties of the quartz and the frequency shifts. And then obviously if we have the mass, we can just divide it by the area of the deposition, and we can get the thickness, So that's one basic simple application of the quartz crystal microbalance. And similarly, we can use it for more interesting things. We can use it for sensing. We can use it as a biosensor, essentially. We can use it for sensing small molecules. So now to sense whether a molecule that we're interested in is present in a given sample, we can functionalize the crystal in a way that we can make only the molecules that we're interested in, bind to them. So this example shows streptavidin, which is a protein. We then construct a little microfluidic setup so that we flow liquid over the quartz crystal, which is functionalized with whatever it needs to be. And as we flow the sample, we monitor what happens to the frequency parameters. So here, as you see, this is the baseline. This is actually from one of the papers that our group has published. This is the baseline, and as we flow streptavidin, we see the frequency shift going down. So the mass binds, the resonance frequency decreases. This is the curve of dissipation, but it's not so important for this application. So that's one application sense. And also in our group we have used it for bacteria detection. It can be used for biomarker detection. There's a lot of possibilities. And this I'll just show you an industrial application as well. This is by a company called Violin Scientific, and they have this interesting idea of evaluating cleaning methods, evaluating different detergents using quartz crystals as well. So switch my screen here. Just to confirm, can you see the video?
Yeah, the video is visible.
Okay. So I'll just show you a little part of it so you can get an idea of different applications. So here they have different quartz crystals that they cover different surfaces. For example, glass, stainless steel, and then different potential plastics, soils, and they have this nice setup here. And what they do is they will now apply different detergents, washing programs, and they will monitor with the QCM how effective are those washing programs. So as you see here, they're adding detergent, red dots, and the detergent removes the soil, and we can see in the background the graph of what's happening, of what's being measured by the QCM. The thickness of the soil decreases, so we know that the cleaning is successful. And by then looking at those curves, we can evaluate different detergents, different cleaning methods, how quick they are, how successful they are. So that's just an example of an industrial application. It's quite interesting. Okay, so this was using QCM for mass sensing, but then when we use quartz crystals for any sort of applications, usually they're also immersed in some sort of a liquid. So, for example, for the streptavidin example I showed you, they were immersed in PBS, which is a buffer solution. So now let's look at what actually happens with the liquid when we put it on the quartz crystal. I have another animation here. So this is the quartz crystal. The yellow bit is the gold electrode, and say this is water. And then this graph, it shows you what happens with the water at the distance away from the quartz. So as you see, exactly at the quartz surface, the water sticks to the quartz and oscillates with the same amplitude. But as we go away, the amplitudes diminish until they basically go to zero at some distance. And this is because of the way the water layers shear against each other. But now, how are the vibration parameters affected by this phenomenon. And so this is what you have seen in the previous animation. The velocity of the water decreases with height, and this was measured by Kanazawa. That's why at 1 Kanazawa unit, we say that the amplitude of the water has decreased by E times. So that's it decreased by around 70%. And this Kanazawa unit, it's dependent on the viscosity of the liquid and the viscosity, the density, and also the frequency of the quartz crystal. And for 14.3 megahertz quartz crystal with water, this distance is only 140 nanometers. So when you go farther away from the surface, the water is not affected. And how the vibration parameters are affected is the resonance frequency decreases because there is some mass coupling of the water with the quartz, because as you've seen on the surface, the water moves with the crystal. So the crystal sees it as additional mass moving. And there will also be additional dissipation, because the water layers, they're shear against each other, so the energy is dissipated, it's lost. And the interesting thing is that the gamma, the increase in the dissipation, is the opposite of the decrease in frequency. So you can see how the dissipation, how the dissipation is related to mass coupling. And I'll just show you by a simple example using 2 different liquids of different viscosity. Here I used ethanol and water. This is the little setup. So we pump the liquid for a microfluidic setup over the quartz. And first we pump water, we take some scans, then we pump ethanol, take some scans, and see what happens. And if you remember the resonance curves, this is the current drawn by the electrode, this is the frequency, this is the drive voltage frequency. The blue is the frequency of the water, is the curve for the water. Orange is ethanol. So because the viscosities are quite similar, as you see here, it's only slightly larger for water. The change is not that visible, but you see that the maximum, that the peak has decreased for ethanol and also moved a little bit to the left. So that's shown here. The resonance frequency fell from those first 2 scans are water, those second 2 scans are ethanol. And the frequency decreased. Gamma, on the other hand, the dissipation increased. And as you've seen in the previous Kanazawa equation, that the frequency shift should be opposite to the gamma shift. And if you look at the numbers here, they are almost exactly opposite. So that's how the liquids influence the vibration parameters. And by the way, those changes will be different. This is for Newtonian liquids. If we use liquids that are non-Newtonian, viscoelastics, these changes will be a bit more complicated, but more on that later. So to summarize, quartz crystals, quartz crystals are electromechanical resonators. By interfacing them with electronics, we can measure their vibration properties, and then using those properties, we can find out about the nature of things that we put on the crystals. So why, you might ask, is this of interest for batteries? I will now give it over to Chris.
Hi.
And he will go over.
So battery is a charge storage device, and essentially when you charge it, electrical energy is being converted into chemical energy, and in this form the energy is stored. And upon discharging, you again convert chemical energy into electrical energy and use it to power whatever device you want to power. Now the 2 main types are primary batteries, which can only be used once, and secondary batteries, which can be used several times. Most of the batteries currently on the market are based either on lead or on lithium, which have got disadvantages. So an alternative to this could be an aluminium battery. You are very familiar with aluminium, it's everywhere around us. It's a widely used, cheap, and easy to recycle metal. So what happens during the operation of the battery? Ions travel between the anode and the cathode. Yeah? But obviously, ions, apart from charge, do have some mass. So it's essential for us to measure mass. And as Jakub already explained, quartz crystal microbalance is a very efficient way of measuring mass. So an electrolyte is a reservoir of charge-carrying species, which are always called ions. The cations and anions, their total charge is always equal when the battery is in the stable state. An electrochemical window is a potential range within which the electrolyte can safely operate, and if you exceed that, the battery will start to degrade. So this would happen, for example, if you overcharge a battery, it might eventually explode because you exceeded the electrochemical window. So this is a very important parameter of the electrolyte. So most of the batteries currently on the market have got what is called classic electrolyte. So for example, in your car, most likely you have a battery which is filled with aqueous based electrolyte, which is basically diluted sulfuric acid. Now they do have some advantages, like high conductivity, but they are corrosive, like sulfuric acid one. The propylene carbonate based electrolyte, which is used in lithium batteries, is flammable, and they're all prone to leaks. On top of that, they have for alternatives. And one alternative to that are ionic electrolytes. So they are based on what is called ionic liquid, or their cheaper alternative, deputectic solvent. Now, a lot of research has been done on this, and although these have got low conductivity, they are non-flammable, less prone to leaks, and they have usually wide electrochemical window, and quite often they are not that toxic as the classic electrolytes. Now, when we want to study a battery, we need to apply some electrochemical methods. So first thing we need to know about the battery is the electrochemical potential. So, for example, if you buy a battery which is 1.5 volt classic AA battery, its electrochemical potential is quantified using the Nernst equation. So that's how people know what type of materials in the anode and in the cathode and in the electrolyte will give you specific potential for a battery. Now, if you look at this equation on the left briefly, you'll see that there is a value F, which is the Faraday constant, and this is charge present in 1 mole of elemental particles. Now, mole essentially is mass. So to properly study electrochemical systems, one needs to measure mass, hence the application of quartz to do that. So very often, when people want to study electrochemical systems, they use a technique called cyclic voltammetry, and essentially, you can see in figure 8, this is an application of a potential gradient. So you apply rising and then decreasing potential to your electrode, and you do that in cycles, and you observe changes in current. So what you apply is in the figure A, and what you see is in the figure B. You see how your current changes over the potential. And depending on what you have in your system, you'll get several different, what they called voltammograms. So then people combine both of these techniques, so electrochemistry and QCR methods, and the result was what is called EQCM, so electrochemical quartz crystal microbalance. Essentially, when people do cyclic voltammetry, they usually use 3 electrode system, where working electrode is where all the reactions take place. Counter electrode is an inert electrode, and reference electrode provides a reference potential, which is then compared to standard potentials of other systems. So that essentially, reference electrodes provides you with 0 point. Yeah, so you know that your when you know the zero, you can measure the potential of your battery, and then you know that this battery gives 1.5 volt or 3 volts or 9 volts. And in the technique called EQCM, crystal acts as an electromechanical sensor, which allows us to measure mass and viscosity, and it's also a working electrode. So you basically do all your reactions on the crystal and measure mass and viscosity changes occurring there. And then mass and charge data, and charge is current multiplied by time. These are used to calculate what is known as transport number. So transport number essentially is proportion of anions and cations being exchanged, and it's always 1. So if a cation transport number is 0.6, then anion is 0.4. And calculation of transport number is of utmost importance when optimizing the performance of any electrochemical device, not only a battery. And mass changes on the electrode are compared to Faradaic mass. Now, Faradaic mass is a mass that would be exchanged if all the electrochemical reactions taking place in your battery would be 100% efficient. So essentially, if your battery is efficient and you start charging it, all of the current would be used to contribute to mass changes at your electrode. Now, that doesn't really happen in real life, but you can see here some electrochemical reaction where on the left you have pure electrochemistry, so essentially oxidation and reduction. And on the right, you can see the associated mass changes and viscosity and mass changes, and this mass change is compared to the Faradaic signal. So Faradaic mass is not something that was measured. This is mass calculated purely from the current. This is under the assumption that your electrochemical reaction is 100% efficient. And you can see that for this particular system, almost all of the electrical energy was converted into mass changes. You can see in the last cycle, the agreement is almost perfect. And pretty much entire electrical energy was used to contribute to mass changes. So what exactly happens to the crystal when you do the what is called the reduction oxidation cycle? You can see that this is the oxidation state, and now we're going into reduction. So again, this is an oxidation, and peaks are sharp because there is no load on the crystal. During the reduction cycle, metal deposits on the crystal surface, viscosity increases, so there is a very significant damping effect, which Jakub already mentioned, and there is hardly any frequency reading. Again, going back to the empty crystal. Yeah, so you can see these are several cycles, and that's how the data in the previous slide was obtained. So this is an empty crystal, all metal was oxidized and removed from it. Now metal was reduced on the crystal.
So also the interesting thing with this one is that we cannot what I talked about earlier about the frequency, the mass binding and the dissipation increasing. Here we have both. We have mass binding and dissipation, and then we have to model it to determine which shifts are due to dissipation and which shifts are due to mass, so we can accurately determine the transport numbers. So that's part of the work which we are working on right now. So that's really crazy.
So also what one has to consider is something known as dendrite growth. Now this is actually something you guys are all probably heard at some point. So basically, because not all of the electrical energy is used into efficient mass changes and the movement of ions, what sometimes happens, dendrites, which are like sharp metal spikes, can grow on the surface of the anode. Now what happens then, if the dendrite grows and connects anode and the cathode, essentially you get a shortcut, and that causes battery fire. Now this is the reason for fires. If you sometimes hear about a laptop or a mobile phone catching fire during charging. And so this is a problem with batteries, and especially now that there is increased use of electric vehicles, this is a problem that needs to be addressed. So quartz crystal microbalance can be used also to observe the growth of dendrites, and this is something we currently also work on. Now, what is the future of batteries? It's very likely that polymer gel electrolytes will be used in the future. And these are highly viscous substances where ionic electrolyte, like the ones I mentioned before, is mixed with a polymer. There already has been publications on this work, and essentially presence of polymer is thought to prevent dendrite formation, and this will increase the longevity of the battery. So this here is a demonstration of a casing-free polymer gel based battery. Now, what is interesting about that battery, that here the thick polymer holds the battery as a cylinder with anode and cathode being immersed in it, and this is only wrapped in a plastic foil to hold the battery together. So basically, battery like that should provide more energy per weight, because you bypass all the need for a heavy casing, which is very, very common in a lithium or lead acid battery. Here, the polymer gel, which is an electrolyte, is strong enough to hold the battery in the form of a cylinder. So essentially, how we have created that battery, we coated anode and cathode in the polymer gel and then roll them in sort of cylindrical shape, wrap it in the plastic tape, and it stands on its own. So this theoretically could be the future of batteries, which would be much lighter and storing much more energy than the currently available batteries on the market. So these are our acknowledgements. So the whole work was actually inspired about the salvage project, which is a project that was devoted to aluminium battery, and we would like to thank Victor Ostanin of Cambridge University. Any questions?
So thank you for your attention, and I'd like to hear questions if you have any.
Okay, so this was like really innovative. Like, I like the idea of how you used resonators to map out the processes going on inside the batteries. So there are a few questions. One is, can you please elaborate more on the deep eutectic solvents and like what makes them cheaper?
They are based on widely available chemicals. So I put references to each slide that I was presenting some work. So no, going back. So I suggest you read that reference here. This is basically the reference to that deep eutectic solvent which I have shown in this publication. And deep eutectic solvents were conceived, I think, in 2002 by Professor Abbott, and this is a paper from his group. And you can see that this particular deep eutectic solvent is based on urea, which is essentially a fertilizer. So the whole point of using deep eutectic solvent is that they are based on widely available and affordable and usually safe materials. So they beat other electrolytes first in the term of cost, and that is quite important if you want to apply these electrolytes on a wide scale.
I would like about that. Like, how can QCR be commercially used? I mean, in batteries, you can use it to check the formation of spikes, but if batteries are commercially sold, like, will QCR be fitted inside it and the users can check it out, because the users might not be conversant about the thing which is going on inside the battery, right? Or does it have to be used by experts occasionally to check?
Well, this is used in fundamental studies. So you use the QCR to study the battery systems until you develop a system where you see that the formation of dendrites does not occur or is minimized as much as possible.
Yeah, so the QCR is not actually used by the end users of the battery. It is used by engineers and scientists in the development stages of the battery. So it's used for testing different electrolytes, different configurations. It's used as a development tool. So that's this application of QCR. But QCR also, if you're interested in general applications, as I shown earlier, sometimes it's used in industry to to monitor cleaning, to test the contamination of different liquids, and also it can be used in the medical industry for diagnosing diseases. And as you mentioned, that obviously the end users they don't have to be conversant in in all of that, but that's not really necessary to use the quartz crystal microbalance for detection, because often we're just interested in basic shifts. So we see like that the frequency is going down, and then if we program it, if we make software, we say that with this frequency associated with this material, it just equals this sort of mass decrease. So for actually commercial purposes, the quartz crystal resonators can be really simplified and made pretty intuitive.
Okay. And so in that piezoelectric sensors, we are using gold electrodes, right? So can we, like, why do we use gold? Like, can we use a cheaper variant? Because it might make it more costly. I don't know about if it is very small, so it might be cost effective, but.
Well, the most commonly used crystals are coated by gold, and you can have them coated by other materials. The thing is, gold is usually quite resistant chemically, and that's why we use it. Also, it's a good conductor of electricity. But you are right, quite often platinum or molybdenum coated crystals are used, and these are also used in electrochemistry, not to study different systems. We just use these because we are familiar with that, and the whole object here was to be able to study the electrochemistry of a battery, and especially the viscous electrolytes and the exact processes that happen here. Because remember what Jakub initially showed in one of his slides with water and methanol, where essentially these are liquid of two different viscosities, yes, but their viscosity do not change. Now, when you deal with a battery, this is not the case. So electrolyte starts with one viscosity, and then its viscosity changes during the process. Yes, so they have variable viscosity, and for example, in here you can see that not only mass but also viscosity changes, and that to quite a lot. So QCR is a very good tool to study these type of processes.
And can QCR be used in measuring the decay of organic polymers used in solar cells? Like, is it cost effective to use these sensors in organic solar cells?
Well, maybe not to be built into a solar panel, but definitely this is used in fundamental studies. There's plenty of literature on that. So EQCM is very, very good tool to study any electrochemical system, where essentially instead of using standard working electrode, which often can be a platinum wire, you just use your crystal as a mass and viscosity measuring tool and working electrode at the same time.
Can you explain the significance of that Kanazawa unit? And because
so I'll show you. That's a very interesting part of the diversion theory. When I learned about this quite amazed at how it works out. So I'll try to go. So to actually get to this, there's quite a bit of derivations to go through. So I didn't include it in this short presentation. So if you want to actually look at the details, if you just search for Kanazawa's original paper, I think this was in 1985, you'll find all the derivations. But I'll try to give you maybe a basic intuition for it. So I'll just show this again. So this is the basic. So this is the basic fact of what happens. This is the basic fact of what happens when we put water on a resonating crystal. So it doesn't slip entirely at the edge. It doesn't slip. It moves exactly at the same speed of the crystal. But then, because water, you can see it as sort of layers which shear against each other, and from layer to layer, a bit of this velocity is lost. It's dissipated, and it's dissipated in friction, the internal friction of water, and this the higher the viscosity of the water, the sooner this motion will be dissipated. So now coming to Kanazawa, you see this Kanazawa unit. It depends on the viscosity of the water. So with large viscosities, this Kanazawa unit. Sorry, I may have confused it a bit before, but with large viscosity, this Kanazawa unit actually increases. So let's imagine, say, something has very small viscosity, like close to a gas, right? Like air. Like if you move air at a surface, this motion is not transmitted very far. But if you move something like more viscous, then there's not enough. Then this dissipation will go further, and also what is intuitive, you see it's dependent on the frequency of oscillation. So if you imagine if the crystal moves very quickly, the water doesn't really have time to follow this crystal. If it moves slowly, you can say if it would be moving a plate very, very slowly, a lot of the water will be moving with the plate. But if we change the direction back and forth all the time, then it has moved a little bit, but then it cannot go back. So with increasing frequency, this Kanazawa unit decreases, and it just tells us how quickly this motion will dissipate. So with larger Kanazawa units, this motion dissipates farther away from the surface. With smaller Kanazawa units, the motion dissipates closer to the surface. And this is significant, especially if we're using particle detection, because we have to look at the relative size of the particles. So say if we have a bacteria here, for example, in the quartz surface, a bacteria is more or less 1 micron big. So that's around 8 times the Kanazawa unit. So only a part of this bacteria, if we put it in water, will be influenced by the motion of the water, and the majority of the bacteria will be stationary. So that's just things we have to consider. We look at the Kanazawa unit, how far is the water is moving, and then depending on what we're trying to sense, we have to see what the physics will be. So yeah, I hope this sort of answers your question.
Yeah, that's a really great explanation. Okay, so I will just ask a small mathematical question. In that formula for finding the mass from natural frequency, I mean omega equals to root over k by m, right?
So
So yeah, yeah,
this one, yeah.
yeah. So you are using this to find out the mass, and so I mean to say that if there are more than one layer of material, they will have different stiffness, right? So do you need to account them in the formula? Like gold will have a different stiffness than quartz, say, or copper. So will it lead to any like error? I don't know. Like, do we need to account for that?
Yes, they will have different stiffnesses, and we cannot really. It's very difficult to do an actual mathematical model for every situation that we encounter. So I mean, the idea of this is we do a model which sort of sums up all those stiffnesses, all those dissipations, and sort of averages them out. So this is the stiffness. I mean, because the majority of this influence will be the quartz itself, the stiffness of the quartz itself. But then, depending on what we put on the quartz, this the motion will be slightly changed, and we then assume as the change of this motion is modeled by this generic expression, and that's pretty much the simplest one we can use for this sort of resonators. That's a linear model. Sometimes we can try if we say, because that's all linear, if we think that the nonlinear effects are significant, then we can try to make more complicated models. But for our applications, this tends to be enough. And also often in quartz crystal microbalance, we're not interested in absolute values. We're more interested in changes. So yeah, so just here, like just a simple mass detection. So this is a frequency offset from some values, and we don't need to know the absolute frequency. We just have to know what will be the change. What will be the change of the frequency with binding. But also, if you want to know more about why we can use this, because I showed you this Sauer-Brie equation that you see that the mass is only proportional to frequencies, and it involves some approximations. As you said, we cannot because things have different stiffnesses and so on. But this approximation, it tends to be very accurate for rigid binding and for small thicknesses. So if you want to see the exact derivation and assumptions in that, you can also search for Sauer-Brie's original publication, and then you can go more. Yeah.
I think that's all the questions we have right now. So I will ask Campus Radio to take.
Thank you. Yeah, thank you, Surjit, for handling all the questions. And we have a few general questions which is on the mind of everyone. The first question is, what what was your motivation to work on this area, or what in a way made you interested in this specific problem? If you could tell us about that a bit.
So I previously worked on battery development program, which is described in the acknowledgement slide, and that prompted me to work on the fundamental studies of how exactly the mass and viscosity changes during the the redox cycle, which can be imagined as a charge-discharge cycle of a battery. And you need to know this if you want to understand what's going on in the inside of the battery, to construct a better prototype, and then hopefully that goes into the mass production. So because there is now a lot of drive towards electric vehicles, and a lot of the personal devices now that we use use batteries, and there's increasing demand on lithium, or other alternatives need to be found, and aluminium is one of them. So this can be applied to many other systems. It's just that batteries are now hot topic because of the demand. So
yeah, so for myself, you asked what sort of got me into this work. When I was starting my PhD, I was mostly focused on medical applications of those sensors. I wanted to use them for biosensing. Because I see myself maybe working in the future as in the medical technology industry. But with the fundamentals, and still that's actually my main line of work. But with the fundamentals of vibrations that I have learned, I can now apply it to different different things. And for example, this battery electrolyte work is one of them. So I've met Chris, and Chris was really interested in batteries, and he sort of got me involved in this whole project, and that's how it started for me.
Great. Thanks a lot for sharing that. And the last question of the session would be, what advice would you like to give as established scientist yourself? What advice would you give to undergraduate students who are interested in pursuing research?
Be open-minded. So you can always use people from, use knowledge of people from completely different backgrounds and apply something that was actually devised to study biological systems, and it can be used to study batteries. So the essential mass and viscosity changes, as Jakub has shown, they can be occurring in biological system. It can be some very simple copper deposition process, or it can be something that goes on inside of the battery. So if you want to know more, I suggest you read the references that I put into the presentation, and you'll find out basically what why we're doing this. But if this type of batteries are to be the future, to construct better prototype, a lot of fundamental studies have to be carried out, and that's what we were doing essentially, the fundamental study of what exactly goes on. Yeah. So that was our main motivation.
So yeah, I asked for advice for people starting with science. I haven't really thought about this for too long yet, because up till now I was the one usually asking for advice. But yeah, one thing I would say, maybe if you're when you're beginning with scientific work, not only PhD projects, but also undergraduate projects, it's really helpful to sort of focus on the fundamentals, on scientific fundamentals, like really going deeply into physics and mathematics of things, and just go really slowly with that. Just go really slowly until you really have an intuitive understanding of concepts. And what this does is it gives you really great power to then apply your really fundamental knowledge to a variety of different concepts which on the on the outset may seem to be unrelated. So I would say that that's a really good mindset to have. That once you learn something, keep asking yourself questions, try to go deeper, try to maybe explain it to someone else, because I think, as someone said, if you cannot explain something to another person simply, it means you don't really understand it yourself. So
Exactly.
yeah, I think this attitude might be helpful.
Thank you so much for the invaluable insight, and I'm pretty sure that all the students will appreciate it here. And we'd like to thank you, Dr. Jacob and Dr. Chris, for taking the time of your busy schedules and being present here. Also, I'd like to thank Sritama for introducing, and Tanishta for helping us finding these wonderful speakers. And we'll just try to, I mean, whoever are present here can show your